All right. Hi, everybody. Welcome to Chapter 13, Sections 2, the lecture on this particular topic of colligative properties. The lecture questions that I want you to answer are at the end of our lecture. Please make sure as you go through, you're taking notes on the lecture itself, and then at the end, answer those questions, and then you will submit those via the form that was sent out earlier this week. All right, so let's get started. This is going to be our topic of colligative properties, which are going to be properties of solutions that depend on the solvent identity and the amount of solute particles present, but not on what the solvent is, or on the solute. So in other words, we don't necessarily care about sugar versus salt, but we do care about the molality of the sugar that's present. And so we'll see how to do that. We're going to start with vapor pressure lowering. We're going to move into freezing point depression and then boiling point elevation. So freezing point depression meaning lowering the freezing point of a solvent, pure solvent, and boiling point elevation meaning raising the boiling point of a pure solvent. And then finally we'll end with osmotic pressure. All right, moving on to vapor pressure. So our first colligative property. A non-volatile substance is going to be defined as one that is not very good at becoming a gas under whatever conditions it's currently sitting at. So if we think about this, sugar water at maybe 25 degrees Celsius, so kind of cold, room temperature for a liquid, but at that particular temperature, the water is probably not going to become gas unless something is done to it. So unless something is added to it or it is changed in some way. So that being said, the boiling point and freezing point of a solution is going to be what we're going to examine in a closer way. And so when we talk about boiling point elevation and freezing point depression, what we're really talking about is the ability of that particular solvent to change its boiling point and its freezing point. And so we're going to see here on a graph that the vapor pressure of a solution, which is the thing on the y-axis, and the temperature on the x-axis are the two things that are being compared here. So the black line represents the pure solvent, and then this is actually water. So the pure water solvent, in this case, boils at 100 degrees Celsius, freezes at 0 degrees Celsius. And what happens in the course of adding a solute to that pure solvent is going to be this change in boiling point. So by doing that, what we're doing is we're actually taking this curve and we're moving it downward. We're shifting it down. And when we do that, what happens is at 1 atmosphere of pressure, which is where we talk about boiling and freezing points, we see that the freezing point of the solution shifts to the left, which means it goes down. And we see that the boiling point actually shifts to the right, which means it goes up. And so we're going to examine these two a little bit closer. And what we're going to do is we're going to look at how is that even possible? What's happening at the molecular level? So first thing to know is that in pure water, there's nothing for water to do other than interact with other water molecules. So there aren't that many interactions occurring. When we add a solute to it, things change up a little bit. Water has to hydrate or surround those different molecules that get added to it, which actually just occupies a lot of its energy or its ability to interact with each other. So instead of having more water molecules being able to evaporate over the solvent, we actually have fewer of them. And that's how that works when we talk about a non-volatile solute that's being added. Now, non-volatile, again, means not going to easily become a gas. So if we add a solute that isn't very good at becoming a gas to water, then we're actually going to lower the ability of water to become a gas. It already wasn't that great at it at different temperatures, but still. So we're going to look at freezing point changes first. And we have to introduce two concepts. The first is that the actual freezing point depression equation is a delta TF equation. And down here at the bottom of the screen, you see that it has two terms. One is a lowercase m, that is an italicized m, which actually stands for molality. And then the other is the K sub F term, which is the molal freezing point constant. So we have to take a constant value, which is related to the solvent, and a molality, which is going to be related to the solute and the solvent, and we're going to multiply them together to get the change in the freezing point. Once we have this delta T of F, we're going to subtract that value from the original freezing point, the normal freezing point, if you will. So we're going to do a practice problem with this information. But first we want to see how do some of these normal values actually happen. So where do these mole freezing point constants come from? They've been measured already. So anytime you see the term constant, remember it has to come from a table of some kind. So we're going to take the normal freezing point of water, which is 0, and we're going to introduce how to change that freezing point using the mole freezing point constant, so the Kf value, and we will see this table a few times in this lecture, and we're going to use that formula that we introduced in the previous slide to do a practice problem. So here is our question. It says that we have 17.1 grams of sucrose with the formula given and 200 grams of water. Our goal is to figure out the actual freezing point of the solution and the freezing point depression. So there's 2 problems in this one. So to start, we're actually going to outline some information. The first is what we've been given. We were told the solute mass and the formula. We were also told the solvent mass and identity. So the first thing we want to do is we want to get the freezing point depression. So we want that delta TF. In order to do that, we need to get our amount of solute into moles because we're going for molality. Remember, molality is moles of solute over kilograms of solvent. So we're going to get our solvent in kilograms. We're going to get our mass of solute into moles by taking the mass and dividing by the molar mass to get the number of moles. We're then going to take the amount of solute in moles and divide by the mass of the solute that we were given. And remember that we want that mass in kilograms. So that's where this extra 1,000 over 1 kilogram comes from, conversion from grams to kilograms. And when we do that, then we're going to plug in our values for delta TF. So we're going to take the KF from a table, multiply by this molality that we're going to calculate, and we're going to get delta TF. From there, then we're going to figure out what the freezing point of the solution is by taking the freezing point of the solvent and adding that delta T sub F. Okay, here we go. So first things first, we calculate moles. So we take our 17 grams, divide by the molar mass of C12H22O11, and we get this number of moles. Then we take that number of moles and we divide by the kilograms of water. And in order to do that, we have to convert those grams of water to kilograms. So that's where this extra term comes from, is converting from grams to kilograms. Remember that you can cross off what you don't need. So the grams and the grams get crossed off here, and then we're left with moles over kilograms, and that gives us 0.25 molal as far as the molality of the solution. So that's the first part. The next part is to do the delta TF calculation. So in order to do that, we're going to take our molality of the solution and we're going to multiply by KF. And from the table, the freezing point constant is going to be negative 1.86. So we are going to keep the negative number and we are going to multiply that times the 0.25. Then we get this negative 0.465 degrees Celsius. So that's the answer to part A, is just what the delta T is. The change in the freezing point is going to be the freezing point depression. The second part that we're going to do is we're going to take the original freezing point of the solvent. For water, it's 0 degrees Celsius from our table, and we're going to add the value that we just calculated because that's the impact of the solute that we added on the solvent. And when we do that, we get a total freezing point, because 0 plus negative is going to be negative, of negative 0.465 degrees Celsius. So our freezing point went down when we added this sucrose to our water pure solvent. All right, from there, then we're going to do a similar calculation for the boiling point elevation. But in this case, we're actually going to use a different constant. We're going to use the boiling point constant. So KF is the freezing point constant for molality, or the molal freezing point constant, and KB is going to be the molal boiling point constant. And when we're doing this calculation, remember, when the first part is always going to be figure out what the molality of the solution is, multiply by the KB, which comes from a table since it's a constant, and then we're going to get the change in the boiling point. And what we're going to do is we're going to add that to the normal boiling point of that solvent. So again, values from a table. So here's our practice question. It's going to be, what is the boiling point of a solution made from 21 grams of a non-electrolyte solute and 400 grams of water? And in this case, we aren't told what the solute is, but we are given the molar mass, which is all we need. So the molar mass of the solute is going to be 62 grams. We're going to take exactly the same approach. We're going to figure out what the delta TF is by getting the molality first. So we're going to take the mass of the solute, divide by the molar mass to give us moles of the solute. Then we're going to take those moles of the solute and we're going to divide by the mass of the solute in kilograms. So in order to do that, we have to convert, remember. That molality is going to be the lowercase m in our equation that we're trying to get to, and Kb is going to come from a table. Once we have delta T, then we're actually going to calculate what the final change or the final boiling point is by taking the delta T and adding it to the normal boiling point. All right, so let's do the actual math here. So we're going to take our 20.1 grams of solute, divide by the molar mass, get the number of moles. That's the first part. Then we're going to take those moles and divide by the kilograms of water. Now remember, in order to go from grams to kilograms, we're going to multiply by 1,000, divide by 1. So we're going to cross off the grams, and we're going to be left with 0.810 moles per kilogram, which is the molality, M-O-L-A-L. The molality of that solution is then going to get multiplied by the, it's the same thing. You're going to take the molality of that solution, you're going to multiply by the given constant of the TB, which given here is for water 0.51. We're going to take that 0.51 multiplied by the 0.810 molar or molal, and we're going to get 0.41 degrees Celsius. And in order to get our final answer here, the final boiling point, we should take this 0.41 Celsius and add it to the normal boiling point for water. So we should take the 100 plus 0.41 and get 100.41 degrees Celsius for the final boiling point of this particular solution. All right, the very next topic that we have to talk about is osmotic pressure. And osmosis and diffusion are going to be ones that we're just going to kind of revisit. We've talked a little bit about them before. You've seen them in biology. These are not new concepts. But what we talk about with osmotic pressure is osmosis first. So the ability of something to pass through a membrane is going to be referred to as osmosis if we're talking about solute, solvent, and a lot of times water. So with osmosis, we talk about the movement of solute through the membrane, the movement of the solvent, through a membrane from where a lower solute concentration is to a higher solute concentration. We're going to see a couple diagrams. Diagrams tend to really help with osmosis, so I'd like you to pay attention more to those, but just understand that osmosis is the movement of water, and then osmotic pressure is going to be the pressure that has to stop the osmotic pressure. So that pressure has to be present to stop the osmosis from happening. So think of osmosis as the movement and the pressure as the stop block, right? Like the cap on the tube. So when we talk about this, we want to look at a couple of things. First is, here we have a diagram where on the right side of the diagram, we have pure water, straight up nothing else. On the left side, we actually have a bunch of solute particles, and we have a very low concentration of the solute particles on the right, aka 0, and we have a high concentration of the solute molecules on the left. So what water is going to do is it's going to move from low solute concentration to high solute concentration, and it will continue to do this indefinitely, right? These water molecules will all move over here because there's nothing keeping them from doing that. There's nothing attracting them to this side, except for what we call osmotic pressure. So there is this limit to the movement of these water particles that is presented to this particular system by pressure. So when we talk about pressure, we talk about, in general for us, as atmospheric pressure. So what stops the water from moving any further is typically going to have to do with the amount of air pushing down on the top of those solutions. From there, we can talk about colligative properties. I don't know why it's putting these numbers in there. And when we talk about these colligative particular properties, we're going to go into our electrolytes. So we talked about electrolytes a little in the previous chapters. For now, we just want to know that electrolytes are going to be kind of similar to solutes. They're going to lower freezing points and they're going to raise boiling points, but they're going to do it more than a non-volatile solute would. So for instance, salt water, so Na and Cl particles are going to break apart. We're going to get positive sodium molecules and negative chlorine molecules floating around in a solution. Those are actually going to change the freezing point and boiling points more than we would have predicted for something like sugar, which doesn't break apart once it hits water. So, and this has a lot to do with the number of particles that they're going to create. So for instance, if we talk about this particular solution, we take this sucrose molecule, we add it to water, and we still end up with just the one sucrose molecule, or 1 mole of sucrose molecules present at the end. If we look at something like calcium chloride, calcium is going to take calcium and chlorine, and it's going to become 1 calcium atom and 2 chlorine atoms. And that's going to be 3 particles, right? So for every one of these, 3 of these exist, which means we actually raise the number of particles for every mole of our compound that gets dissolved. And the very last one is going to be our sodium chloride, which takes the NaCl and breaks it into 1 Na and 1 Cl. So it's actually going to have 2 molecules. Ignore these numbers. I don't know why they're there. They're wrong. So remember, CaCl2 becomes 1 Ca, 2 Cls. That's a total of 3 moles of particles from 1 mole of particles. The sodium chloride is going to be NaCl, 1 mole of particles, that becomes 1 Na and 1 Cl, so 2 moles of particles. This is something we kind of covered a little bit in a previous chapter where we were trying to estimate how many particles were being created over the course of a reaction. All right, so our colligative properties are then going to depend on the total amount of particles present at the end of a dissolving process. So for instance, dumping sugar into water is going to result in 1 mole of particles that gets created, but dumping calcium chloride into water is going to create 3 moles of particles that get created. Sorry, I don't know why it exited for me. So what we're saying is that the number of particles as it goes up will have a bigger and bigger impact on the colligative properties, the freezing point, boiling point, vapor pressure lowering, all of that stuff. So you would expect that the effect on the colligative properties would be twice as large for something that breaks into 2 parts than for something that doesn't break apart at all. And so let's look at a table. So here we have KCl. The molality of that particular solution, when KCl breaks apart, it breaks into 2 parts, so K and Cl. And what it does is it changes the delta T, so the change in the freezing point is about 1.85. Down here with BaCl2, which breaks into 3 parts, and we take that 0.1 molal, so we're comparing the first 2 of each row. The change in the freezing point is a little bit larger, so 2.53. Whereas with MgSO4, which is going to break into 2 parts again, you're going to see similar to the first one, the change in the freezing point is, not as high as it would be if it were 3 parts. This is all going to be based on the number of particles that they create when they're in solution, so the molality, right? It's all going to be based on the solvent that they're dissolved in. For this one, this is all water. And these are all values that have, for the most part, for the K values have been measured, but the change in the freezing points are things that we have to calculate using our delta TF and our delta TB equations. Okay? These you would predict one thing, and then when we measure them, we get kind of different answers. A lot of times what we're not taking into account here are intermolecular forces, something we talked about way back when. How attracted the different particles are to each other, how attracted they are to the water molecules, what are some of the intermolecular forces that are at play here. And in doing this particular change in freezing point and boiling point, those are forces that are not necessarily taken into account according to the methods that we have actually discussed so far. Now, there are further discussions on this, and we will not focus on that in our chapter, but just understand that this all comes together with our intermolecular forces section, in that when we talked about how our molecules behave when they are in solutions, one of the things that we did discuss is how intermolecular attractions can really screw up any predicted interactions. And one of the things that we want to pay attention to is higher charge or lower concentrations, and how higher charges and lower charges or bigger molecules versus smaller molecules all can actually impact that final result of a change in a freezing point or a boiling point. That brings us to our very last part of this lecture where you answer the questions. So you're going to go through and you're going to tell me what the 4 colligative properties are and tell me why they're classified as colligative properties. Remember the definition of a colligative property, that should help you. The second question has you discuss the differences between expected and experimentally observed properties of electrolyte solutions. So just kind of why do we expect one thing, but we really experiment and we find something else happens. And that is all. When you're done, you're done. Have a great day.